Parking meters drain faster in the rain than from any thief. That's why the dome exists. Not for looks, but to shed water before it destroys a $400 piece of street hardware. In this video, why the dome shape was an engineering decision. What happens when water gets inside a meter? Why flat-topped meters failed in the field? And one city that learned this the hard way. When Carl McGee invented the parking meter in 1935 in Oklahoma City, his original prototype looked a lot like a small post with a clock face bolted on top. Functional, ugly, flat. The city installed 174 of them on July 16th of that year, charged a nickel for an hour, and declared it a success. What they didn't talk about was how many of those meters failed within the first 2 rainy seasons. The assumption most people carry about parking meters is that they're built the way they are to look official, authoritative, maybe a little like a small fire hydrant. That's wrong. Almost every exterior design decision on a parking meter comes back to one problem: keeping water out of a mechanical device that lives outside 24 hours a day, 365 days a year, in every climate on Earth. The dome solves a physics problem that a flat top cannot. Rain doesn't fall perfectly vertical. It falls at an angle, it splashes up off the pavement, it pools. A flat surface on top of a metal housing creates a standing water situation. Water sits there. It finds every seam, every screw hole, every imperfect gasket edge, and it migrates inward through capillary action. Once moisture is inside a mechanical meter, you get corrosion on the coin mechanism, swelling of paper components in older units, and, in freezing climates, ice expansion that cracks housings from the inside out. A dome shape has no flat plane for water to collect on. Any water that hits the top immediately runs to the edge and drips off. The contact time between water and the housing drops from minutes or hours down to seconds. That's not decorative geometry. That's the same principle that makes a pitched roof work on a house, scaled down to a 14-inch piece of cast aluminum sitting on a city street. Here's the counterpoint that makes this interesting. Indoor parking equipment, the kind you find in parking garages, ticket dispensers, in covered structures, is almost universally flat-topped or boxy. Square corners, flat lids, straight edges. Because water is not the enemy inside a structure. When you remove the rain problem, manufacturers default to cheaper, easier to manufacture rectangular housings. That comparison tells you something important. The dome isn't a style choice that got carried over from tradition. It's a direct response to outdoor exposure. Companies like Palm Inc., Duncan Industries, and later IPS Group all maintained the dome profile across decades of redesigns because field data kept making the same argument. Flat tops failed faster. Some modern smart meters, the solar-powered ones with digital displays you see in cities like San Francisco and Denver, experimented with low-profile rectangular tops in early prototypes during the 2000s. Most of them added a slight convex curve before going into full production. The engineers rediscovered the same lesson McGee's successors learned in the late 1930s. There's a deeper reason the dome shape persisted that goes beyond just shedding rain. It's about vandalism and maintenance economics. A dome is harder to use as a surface. A flat-topped meter becomes a convenient shelf. People set coffee cups on it, flyers get taped to it, and gum, wax, and adhesive residue build up in a way that eventually works into seam lines. The curved surface discourages that. There's nothing to set a cup on without it sliding off. It's a passive behavior shaping design, the same logic behind curved benches designed to prevent lying down. On top of that, the dome houses the mechanism that matters most. The time indicator dial and the coin slot are positioned on the face, but the dome protects the upper gasket, the single most critical seal on the unit. On a Duncan model from the 1960s, that upper gasket ran about 18 inches in circumference. If it failed, the repair cost more than the meter earned in a month. The dome extends the life of that gasket by deflecting UV exposure and pooling water simultaneously. The city of Chicago installed roughly 36,000 parking meters before privatizing the system in 2008 in what became one of the most criticized municipal deals in American history. But the hardware failure record before privatization tells an interesting story. The meters with the most maintenance calls were concentrated in the flat lakefront zones where wind-driven rain came in near horizontal off Lake Michigan. Flat-sided and poorly sealed meters in those blocks failed at nearly double the rate of standard dome-top units in sheltered street canyons. The city's own maintenance logs showed water ingress as the #1 cause of mechanism failure, more than vandalism, more than coin jams. That's a real-world case study in what happens when installation context ignores the weather physics that drove the dome design in the first place. This same logic runs through a surprisingly wide range of outdoor objects. Fire hydrants have rounded bonnets on top for water deflection and structural strength. Electrical junction boxes mounted on poles use sloped lids. Outdoor padlocks have shrouded shackles partly to keep water from pooling in the lock body. Even old-school newspaper boxes, the ones you still see outside diners, have a slight forward cant to their tops, so rain runs off the front instead of seeping into the hinge. Anywhere a mechanical system lives outside unprotected, you'll find some version of the dome principle at work. Water is the universal enemy of mechanical precision, and the curved top is the oldest, cheapest, most passive solution. The dome on a parking meter isn't there because someone thought it looked good in 1935, or because it became a municipal icon. It's there because water destroys mechanisms and a curve costs nothing to maintain. That's the principle. Passive geometry is cheaper than active waterproofing. If this is your kind of thing, the engineering reason behind objects you walk past every day, object theory drops new ones Monday, Wednesday, and Friday. Wednesday,